I'd like to welcome everyone to our May meeting for our Sacramento SMPTE chapter. I'd like to note that this meeting is being recorded and will be posted to our YouTube channel. In order to find that, you can search YouTube for the Sacramento SMPTE section, and you will find us and links to all of our videos. So I'm going to start with a brief presentation here just to cover some housekeeping items. And then we'll get on to the topic of the day, which we've got Norm Hurst here, who wants to talk about the subject of let's talk high dynamic range and wide color gamut. So we're happy to have Norm here, and he'll be joining us in just a few minutes. So as a reminder, this is our current Sacramento SMPTE board. And we've got our chairperson who's on the call, Remington Maxwell. We've got our past chair, Dom Jackson, secretary and treasurer, Mona Smothers. Sean Case is, for our managers, we've got Sean Case, Bob Huddleston, Patty Leonard, Gil Mazzy, Paul Turner, and myself, Tim Walker. We've had some elections recently, and the election results are in for our chapter. We've got some news to present here. So for the one-year term of chairperson, we've got Remington Maxwell, who's going to hold the roll down again for another year. Thank you, Remington. We've got the secretary-treasurer position for a one-year term being held down by Mona Smothers. Congratulations on your re-election, Mona. And the managers are a two-year term, and we've got Bob Huddleston from AJA Video Systems, who's serving another term, and Patty Leonard also serving another term from Grass Valley. And Robert Erickson, who is a new manager. We'd like to welcome him to the team, and looking forward to having him participate in all of our stuff. And Sean Case has been a great manager, but will not be coming back for another term. So we'd like to thank him for all the help he's provided us during his time with SMPTE. So I'd like to remind you about the different memberships that SMPTE offers. So there's 4 different levels of memberships. For individual memberships, we've got the executive, professional, the recent grad, which is good for the new hires at different companies, and student memberships. And then we've got a couple other options for retired, associate, life member, and then the free one for the people that are SMPTE fans, where you can still access some great SMPTE content. For more information on all of those, you can go to the SMPTE website at www.smte.org. Covering a couple things that are new at SMPTE. So some of you may have received the May edition of the SMPTE Motion Imaging Journal, which comes with your membership. And by the way, the memberships help us pay for different things, including some fun things like this and some coasters and things, and also for some of our social events that we do once in a while. And so we do encourage you to become a member. And as a member, we've got the ability to nominate our co-workers and people in the industry for some awards. And the award nominations are open. So I'll just kind of read through this here. SMPTE confers a number of honors and awards annually to recognize the achievements of industry luminaries, outstanding volunteers, and students. Unless otherwise specified in the Governance Ops Manual, any member of the SMPTE Society is entitled to nominate individuals as candidates for Society awards. And the full listing of awards can be found on the SMPTE website that I mentioned earlier. Next, we've got SMPTE Plus, which is a new thing for SMPTE. It brings you access to the hottest media technology content and to the technologists who make it happen through a hybrid of interactive events and on-demand content. For each SMPTE Plus event, you'll be able to meet with other SMPTE Plus subscribers to discuss their content, hear live presentations, and engage in Q&A with speakers and panelists. SMPTE Plus is free to SMPTE members, so go to this website here. The URL is on the screen for more information. So without further ado, we've got Norman Hurst, who's going to close out the SMPTE presentation season for us. Welcome, Norm. We'll just read through his bio here and we'll get you going. So Norm Hurst is a senior principal research engineer with SRI International. He has been staring closely at TV pictures for over 3 decades. The project he has worked on include D-Cinema watermarking, CCD camera simulations, Sarnoff MPEG Compliance Bitstreams, and the DirecTV and Grand Alliance prototype MPEG encoders and decoders. Lately, he has been developing HDR and wide color gamut test patterns to guide us through the jungle of formats that digital video has brought us. He is a SMPTE fellow and holds over 35 patents. He also received the SMPTE Digital Processing Medal Award and the Camera Origination in Imaging Medal Award. Thank you, Norm, for joining us and presenting to our chapter. I would like to turn it over to you.
Thank you, Tim, and thank you for inviting me. Let's see, I've got a little echo going on here. If you mute there, it'll probably end that. I'm going to share my screen. Any minute now. There it is. You see my screen there?
We can, you're good. Yep.
Just nod vigorously. All right. Good. Again, thank you. And let's get into it. This is me again. You've heard the bio, so we'll skip through this. In 76 to 80, I worked as an intern at the RCA Broadcast Studio Camera Design Group. My supervisor there was Larry Thorpe, who recently retired from Canon after a long career. In the 80s, I worked at RCA Labs in support of their consumer video products. Yes, I worked on video disc. And then 90 to about 2008, I worked with advanced television system design and test at the Grand Alliance and DirecTV prototypes and things like that. And then since 2008, I've been designing video test patterns for professional use. And that's where I come from. I come from that activity today to talk about wide color gamuts and high dynamic range. Here I am trying to pick up a 1 pixel. SMPTE fellow, oh yeah, you heard all this, so we'll skip all that, 3 dozen patents. Okay, so in 2008, I designed this pattern for what we now call standard dynamic range, SDR. We used to just call it video. This pattern was designed to reveal digital TV problems. I noticed that everyone was still using color bars, but color bars had been designed to detect and reveal analog TV problems, and those problems were gone, but it's not like we didn't have problems. We got compression, we got mismatched YUV matrices, lip sync. Color bars won't show you much about lip sync or bit depth. Resolution scaling, we now have multiple resolutions and formats. Chroma subsampling varies from system to system. Frames were dropping and more, all these problems. And I designed this to be no need for a waveform monitor. You could just evaluate it by direct observation. You just look at it and you can tell, since you know what it's supposed to look like when it's right, you can tell when it's wrong. So around 2015 at trade shows, people said, so you're going to make a version for high dynamic range wide color gamut? And I said, sure, not really knowing what I meant there, but of course. So today we'll talk about dynamic range, and I'll clarify why HDR photography and HDR video mean different things. And we'll talk about what kinds of images can benefit from HDR, get a feel for that. What is a color gamut, and what kinds of images benefit from a wide color gamut? What is video? That is, how does a camera make video, and why specifically is there gamma? And how can you optimize the gamma curve? And we'll talk about PQ and HLG, the two coexisting standards for new gamma curves. And then we'll talk about making an HDR test pattern and whether it's sufficient to convert a color space or it needs a redesign, and talk about revealing some of the pitfalls of HDR and wide color gamut. And finally, the OOTF, the optical to optical transfer function, and why you should care. So what is dynamic range? Well, some basics. What is an f-stop? What is dynamic range? What is a nit? So an f-stop, this is a lens thing, you may be aware. There's a ring an iris, controls the iris opening, and it has calibrated click stops. Each stop is it changes the amount of light by 2 to 1. So it indicates a ratio of light. So 3 stops is an 8 to 1 change, which is because it's 2 raised to the 3rd power. It's 2 times 2 times 2. What's with the funny numbers? 1.42, 2.84, 5.6. Well, the numbers, the f-stop numbers correspond to the diameter of the opening, but the amount of light corresponds to the area of the opening, which is the square of the diameter. So if you square these numbers, they're no longer, they're quite clear what they are. They're doubling 2, 4, 8, 16, 32. So if nothing else, maybe you've learned that today. Dynamic range is the ratio of the brightest to the darkest. For a camera sensor, that's saturation, blowing out the whites, down to the noise floor. For a display, that would be the peak luminance to the darkest low light. For the human eye, it's the brightest tolerable light to the darkest perceivable, and is often described in f-stops. What's the dynamic range of the human eye? Well, within a given scene, about 100 to 1, about 6, 7 f-stops. But given the eye's ability to adapt, if you've got a scene that's all dark, you can resolve detail in that once you adapt to it. And you get a scene that's very bright, you can resolve detail in that too, just not simultaneously. But considering that whole range, it's about 20 stops. It's remarkable. What is the dynamic range of a camera? Well, there's CCDs have wells that accumulate electrons from photons. And when a well is full, it can't take any more photons. So that's saturation, that's blown out. And then down to the noise where you can't tell if there's photons there or it's just noise from the device. And state of the art is 14 f-stops or so. What is a nit? It's a unit of luminance, brightness, essentially. Candelas per square meter. Nit is a shorthand for the candelas per square meter. Like you might say click for kilometer, we say nit for candelas per square meter. So you say, oh, my phone has an HDR mode for photography. Well, it turns out HDR is an overloaded term. A phone actually takes multiple SDR exposures and then merges them into an HDR image, but then it compresses the HDR image into an SDR viewable range. So here's what it might do. So a camera might take 3 exposures at different exposure levels. It might take a dark exposure. This gives the details in the brighter areas. And it might take a bright exposure, which gives you details in the darker areas. It pulls it out of the noise. And then you might take a sort of a normal exposure. And then the camera applies some kind of magic algorithm and merges these into essentially a standard dynamic range image that compresses the dynamic range, much as you might compress audio dynamic range. So you could do it that way. There's a lot of algorithms and a lot of knobs you can turn. You can also make something like this as well. So that's when you talk about a camera HDR photography, this is what you're talking about. You can look at it in another way. HDR photography takes a very wide range of input and compresses the contrast down to a narrower range, a standard dynamic range. That's what, and so it can be displayed on SDR. That's what HDR photography does. HDR video doesn't do that. HDR video does something very different. HDR video attempts to take the entire range and convey it to the consumer as is without compressing it, so the consumer can show a true HDR image on the display. Notice I can't show you examples of HDR because you're looking at this on an SDR computer. Anybody that tries, like you see a website and says, well, this is what HDR looks like. If they're talking about video, they're lying, because you can't show HDR on a standard dynamic range monitor. What kinds of scenes can benefit from HDR? Well, scenes that have very bright lights like fire often can be, the highlights get blown out and you won't see any detail in them. HDR helps with that. Sports, consider a football game in the late afternoon when half the stadium is in shadow and half the stadium is in direct sunlight. You get a very, very wide dynamic range. Today, with SDR, you really compress that range using contrast compression. But with HDR, we can make it more realistic. We can show the details in those areas better. It's not just about bright things. So here's a scene from sort of a famous episode of Game of Thrones, where everyone was at home scratching their heads because all they saw was a black screen. And so HDR is also about showing you details in very dark areas and allowing you to resolve details there. Here's another scene. Perhaps you can see this is, sorry, didn't follow that show. This is the lady riding the dragon. Trust me, if you can't see it, that's the lady riding the dragon. Here's another image of a man standing in front of a wall. Now they say, well, you just turn up the contrast and you can see it. Well, you can, but like this, but it's the modeling and the puddling and the quantization errors is just pretty bad. And so HDR aims to fix that, aims to remedy that. So you get good detail down in dark areas. So what is a color gamut and what kind of images benefit from a wide color gamut?
Hey, Norm, this might be a good time for me to pause and just let people know, since I failed to earlier, that if you have questions, you can feel free to put them in the chat window and I can answer, or I can ask Norm at the end. Or if you would like to, you can unmute yourself and ask them real time, and Norm's offered to answer them live. So with that, please continue, Norm.
Thanks. I'll try to answer them. Where was I? So a color, as you know, is represented by 3 values, red, green, and blue. But those values alone cannot nail down exactly what a particular color is, because the values are relative to a particular set of color primaries. Often, like on the web, it's implicit. So the color primaries are sRGB, which happen to be the same as Rec 709. But without knowing what the primaries are, a given set of RGB triplet values do not allow you to know exactly what color you're talking about. The primaries that are implicit are part of a defined color space. So if you don't know the color space, you don't really know what color an RGB triplet represents. So color space matters. So you may be familiar with this diagram. Let's take a moment and sort of walk around it and understand the different parts of it. This represents the colors that humans can see. The horseshoe-shaped curve represents spectrally pure colors, like the colors you get from a laser. And you can see the curve here is marked out in nanometers. This is the wavelength of light. It covers about 1 octave of frequency, of light frequencies. So you start at short wavelengths is blue, and then as it gets longer wavelengths, it becomes green, and then it becomes yellow, and then orange, and then red. And you keep going, it would be infrared, but you can't see that. On this side, it'd be ultraviolet, but you can't see that. The inside part is all the colors that, well, most humans can see. And near the middle is what we call the white point. It's often, there's different standards. Their nomenclature like D65. The white point corresponds to, usually corresponds to the color temperature, which is, it goes back to physics thing. It's the black body radiation of a substance that's been heated so hot it glows. So, you know, if you heat something up, you turn your electric stove on or your heater, it starts to glow red. That's down here it comes up infrared, and then you can see it's glowing red. And then not shown here, there's a curve that follows on this diagram, and it becomes actually white hot, and will continue past that towards blue. if it gets even hotter. So it doesn't really matter what the material is that's hot. But if you heat it up to 6,500 degrees Kelvin, it'll give you this color. That's the white point. The primaries are the corners of a triangle, which are usually somewhat inside of the curve, the spectral locus curve. And the corners of these triangles are called the primaries. And given a set of primaries, you can mathematically describe all the colors, any color that's inside the triangle, but not outside. So inside the triangle is your gamut of colors. And a saturated color. So for instance, if you're on this line that's blue to green, if you're actually on the line, that means the red value is 0. When any color is 0, it means it's saturated. Can't get lower than 0 because you can't make negative light. If you could make negative light, you could make a color outside the triangle by having negative red, but we can't make negative light. If you make a bigger triangle, you have a wider gamut. And this is what's meant by wide color gamut. And a bigger triangle includes more intense colors. So these two triangles are the triangles we talk about, the gamuts we talk about. This is Rec 709, the smaller one that we've been using for years. This is where D65, the white point, is. And then Rec 2020 is associated with HDR. And the primaries happen to be on the spectral locus. They're laser colors. So most monitors can't display this. Laser projectors theoretically can. I've not seen that. But so what colors does wide color gamut add? Well, it adds the colors between these two triangles. So what scenes can benefit from wide color gamut? And well, most everyday colors do fit inside the 709 color gamut, and very few real life colors exceed it. Some examples: flowers can be found that will show you that will benefit from wide color gamut. Some fabrics, a couple of these colors in these, but not all of them, do exceed 709. And also things like neon lights, emissive sources. Neon lights are almost lasers, and other sources like fireworks can generate colors that are very intense, nearly spectrally pure. So it's these sorts of things that can benefit from a wide color gamut. High dynamic range. So as opposed to standard dynamic range, or what we used to call video, it shows more detail in bright areas and dark areas, and the whites are not blown out and the blacks are not crushed. That's really what it's about. Wide color gamut is opposed to, well, what we used to call video. It allows capture and display of more saturated colors. HDR and wide color gamut are independent features. You could define a system with just one or the other, but today they travel together. HDR works without wide color gamut, but wide color gamut does need HDR to work well. And HDR in your cell phone's camera is not the same as HDR video. They're different concepts. So all this sounds like a radical change to TV systems. But is it? Well, in theory, that is how it works. No, not really. And in practice, how we use it, yeah, it is different. So let's review how video works. How does a camera make? Well, video we often think of, well, it's a signal on a wire, or it's a stream, or it's a file. That's video, right? But let's think about where it comes from. Well, of course, it comes from a camera. So let's ask ourselves, how does a camera take light and make the signal on a wire? So here we have a lens, and here we have a box, and we're going to build a camera inside of this box. Right behind the lens, of course, is the sensor. The sensor has colored gel filters over the CCD elements. These filters tend to be proprietary with the manufacturer of the sensor, and the sensor produces raw color signals. And again, these depend on the color filters. A sensor doesn't really have a color gamut. It's a wavelength discerning device. So don't let anybody fool you into saying, oh, it's a 709 sensor. But these raw taking signals that come off these the colored filters have to be converted into one of the standard color gamuts. So that gives us the sort of classic RGB values in a reference to a given set of primaries. This is linear light RGB. Well, then we take that and we run it through a gamma function that stretches blacks, or more generally known as an optical to electronic transfer function, an OETF. And this gives us RGB values we mark with primes to indicate that it's not linear anymore. So wait a minute. Why is there gamma? Well, years ago, I might have told you, well, it's to precompensate for cathode ray tube nonlinearities. Cathode ray tubes have a grid and a cathode, and the applied video has a voltage difference there. And it turns out there's about a square law between the voltage difference and the brightness you get off the face. But actually, even if CRTs were linear, we would have wanted gamma for the whole system. And the reason is that applying a gamma here in the system gives more quantization steps near black, denser quantization steps near black. It's a perceptual thing. Humans are more sensitive to small changes in dark areas than in bright areas. And that's really what this is all about. So to understand this a little better, let's take a very simple system. We take linear light RGB and we quantize it to only 5 bits. That's just 32 steps. And then we look at it. That's a whole TV system. And so quantization could happen in SDI, it could happen in MPEG or H.264 encoding. So what's the transfer of this look like? Well, for the light going in on the x-axis to the code value coming, or the light on the display coming out, we have 32 steps, and each step is the same size. And this is what we would call gamma equals 1.0, or we also say this no gamma, it's linear. But human perception says, I would like to have more steps near black, but I don't need as many near white. So I'd like to trade off. I would like to push some of these steps down near the bottom to make use of them there. How can we do that? Well, oh, and by the way, you would need about 4,000 steps to make a linear TV system look okay as standard dynamic range. That's how dense the steps need to be near black. So what we can do is we can stretch the blacks before we quantize and then put a compensating inverse function after. So these are inverse curves so that the overall is linear again. So let's look at the overall. And now you can see how the steps are very dense near black. This is a gamma of about 2. And the steps are bigger near white. And just by putting in these curves, we've shifted the density of the steps down towards black, just what we wanted. We got smaller steps here and bigger steps there. The use of gamma makes the system a better perceptual match to the human eye's sensitivity, contrast sensitivity. We have a saying, television doesn't have to work, it only has to look like it works. And so that's sort of the basis of all the engineering we do to make television efficient. Back to our camera. So after we've made gamma correction, we're not done. We also convert the RGB to YCBCR or YUV to its friends. Why do we do this? Well, again, television doesn't have to work. It only has to look like it works. Turns out human perception is really good for black and white, not so much for color. It's a rods and cones thing. So we convert from RGB to YUV, where Y is the black and white part and UV are the color differences. And then we throw away the resolution in the U and V. So for 422, it's 2:1 horizontally. For 420, it's 2:1 horizontally and vertically. NTSC was, half a megahertz for IQ and 4 megahertz for the luminance. So that's 8:1. And by the way, heads up, changing the RGB primaries out here also requires changing this matrix a little bit. So there's going to be a pitfall. So after we've done that, we quantize to 8 bits typically, and then we undo all those steps in the display. We convert from the inverse matrix to go from YUV to RGB, gamma corrected RGB. We undo the gamma and we get linear RGB, and then we consider what those values mean in terms of the native space of the display. And so we do that conversion. There's an inverse step for each one of these. And that's a complete TV system. Now, how does HDR change this diagram? And how does wide color gamut change this diagram? Well, it doesn't really. It only changes the parameters in those boxes. So let's go back. So wide color gamut changes the primaries. So maybe from 709 to 2020. HDR changes the gamma curve from 709 gamma to either PQ or HLG gamma. There's 2 coexisting standards now. And changing the color gamut also causes us to change the matrix for converting to YUV a little. And we also, now we send 10 bits to the consumer because we need that as well to make it work better. So it's a combination. The HDR comes from a combination of optimizing the gamma function and also adding a couple more bits to the signal. So HDR wide color gamut makes changes to these things. So how can we optimize the gamma curve? So PQ is optimal and HLG is compatible. What does that mean? So how do you optimize the gamma or OETF, optical electronic transfer function curve for human perception? So traditionally gamma, quote unquote, optimizes the TV system for human perception, as we saw before. But it's not really optimized because they were just using the CRT curve to make cheap TVs. They didn't put in a specialized curve optimized for human perception. The CRT was close, worked pretty well, got us where we are today. But it's not really optimal. And Dolby said, hey, we're not using CRTs anymore. And hey, we've got pretty fancy digital processing. We're not using vacuum tubes anymore to do everything. We could make a new curve that's really perceptually optimized to human vision, because now we understand human vision even better. So they went back to Peter Barton's model of human contrast sensitivity. And Barton's model points out that visibility of a brightness change, contrast change, requires a bigger change at higher brightnesses. Of course, we already knew that, but he quantified it. So he wrote a book on this. So I'm not going to get into this. Don't be worried. He created this fairly complicated model of human vision contrast sensitivity. But the bottom line is, as it gets brighter in an absolute sense, candelas per square meter, that's nits, the smallest step you can see gets larger and larger. And again, that's the basis of gamma, but here it is quantified carefully, and it was verified in human testing, subjective testing. So Dolby said, well, each next quantization step should be just a little less than what you can perceive at that brightness level. So it's a perceptual quantization, or PQ. Again, Barton says it depends on the absolute brightness in nits. And so Dolby went with this and said, well, PQ maps SDI code values to absolute brightness values. This has never been done before in television. Television is always like, well, here's the relative brightness, set your display brightness how you want it. And now Barton and Dolby say, no, we're going to assign particular code values to specific brightness values. So 75 IRE turns out to be 983 nits. So if you ask how many nits is color bars, there's your answer. And 100% is defined as 10,000 nits. 10,000 nits is not like looking at the sun, but it is pretty bright. It's like looking at a naked fluorescent tube. So the linear light in to code value IRE out for 709 looks like this. For PQ, it's much more aggressive near black. And this is the optimal curve, according to Barton and Dolby. And so in 709, you saw this earlier, the steps get pushed more densely down to black. In PQ, that whole process is even more aggressive. And here, I'll look at it. All right, so even more aggressive, and the steps near white are very large. Now, admittedly, this is up near 10,000 nits, these big steps. And Barton says it is true that you aren't bothered by those big steps. So here's three faces encoded as Rec 709, and you're just seeing them as Rec 709 or sRGB. And that looks, hang on, let's look at the chat. And oh, finally, I was seeing a zoom bar at the top. Hang on, I'm lost a little bit. Sorry. Okay, can you see my screen? Okay, I'll assume you can. So here's Rex again, 709. It looks good. It looks fine. It looks correct because it's 709. You're just seeing it as 709 on a computer display. Here's that same image encoded as PQ in the 2020 color gamut, but you're seeing it interpreted as 709. So it looks washed out. PQ was never intended to be watchable or compatible on old TVs. I think you could see that here. They expect it to be properly decoded with an inverse PQ curve. Well, folks at BBC and Arrive said, well, hey, compatibility or at least watchability on existing TVs is important. So we're going to propose a different curve. We're going to propose one where the lower half is gamma, so that's compatible. And the brighter half, the upper half, is going to be a log curve, and that's the HDR part. And make a smooth transition between them so it's one curve. So it's a hybrid. It's a log gamma hybrid log gamma HLG. So the illumination on x-axis and the signal here. So the bottom half is gamma and it's compatible, and the top half is hybrid log gamma. So hybrid log gamma, you see, falls somewhere in between PQ and 709. And so here's what we saw before, 709 as 709, PQ as 709. And here's HLG 2020 as you're seeing interpreted as 709. Is it compatible? Well, we could turn up the contrast. I'll click and you'll see. And there we turned up the contrast. And not bad, right? It looks, it's the whole lower part being gamma works. And but, well, the colors are off because it's 2020 and we're interpreting that as 709. So it looks kind of green here. So the colors are being misinterpreted because they're in a different color space. So is it compatible? Well, there it is. So given all that, how do we make an HDR test pattern? Do we convert the color space or do we need to actually redesign it? So here's the pattern I designed in standard dynamic range, or what we used to call video, in Rec 709. Can we just convert this signal to HDR? Well, isn't HDR really just a different color space? What is a color space exactly? A color space has basically three parameters. It has that triangle, that gamut triangle. So that consists of RGB positions delineated in X, Y, X, Y, X, Y. It has a curve, this OOTF curve definition. So 709, PQ, HLG, and it has a white point, D65, and it has an XY position like the three colors do. And fortunately, the white point's the same in all of this, so we don't have to worry about that one. Well, SDR, our current test pattern, uses Rec 709 for the primaries. It uses an OETF of 709 gamma and a white point of D65. So that's that color space. And what the color space we'd like to convert it to uses 2020 primaries and a curve, either HLG or PQ, depending which kind of pattern we want to make, and the same white point. So we could just convert the color space. What could be simpler? Converting between color spaces is well defined. SMPTE has a recommended practice 177 on that describes the derivation of the color equations. It's a well-written little piece that I've implemented in software to do all this. So here's an example of a block diagram. So let's say we start with 709 code values, regular HDR TV. We want to convert that to PQ 2020. So the first thing we do is we get rid of the gamma. We undo the gamma from the R, G, and B signals. And now we have linear light RGB in the 709 color gamut. Then RP 177 says, convert those primaries to a universal set of primaries called XYZ. Those primaries are this giant triangle, these three dots, that encompass the entire spectral locus. And that's XYZ. Of course, you have to do this in floating point. So now you have linear light XYZ, and that's sort of like a universal color space. And we convert that then from XYZ to the color space we desire, which is 2020 in our case. And then now we have linear light 2020, and now we apply our OETF function that we desire, which is PQ. And now we have PQ 2020 code values. That's how you do color space conversion, basically. And when you're using a LUT, the LUT is an approximation of this process. This is a BT709 to BT2020 PQ converter, albeit a bit naive because, well, it's mathematically correct, but often people don't like how that looks, so they tweak it a bit. But this is the mathematically correct conversion, which is what you'd want to use on a test pattern. So let's use it. So we take our 709 test pattern and we run it through an RP177 based color space converter, and we get this, and it's washed out. Well, because we're looking at it at 709, we'd expect that. Here's the problem. I converted this mapping 100 IRE on this side to 100 IRE on this side. But that means we're mapping 100 IRE SDR to 10,000 nits. So that means it's basically a 10,000 nit, it's just a really bright image. So most displays—
Can I interrupt and ask a question here? Just for clarification, the relationship of IRE to nits, can you describe that so we can better understand?
Okay, so in SDR, it has our SDR code values have a range from 0 IRE to 100 IRE. And then I said, okay, whatever in that image is 100 IRE, we're going to map that to the top of the PQ curve, like it's on the top of the 709 gamma curve. Well, the top of the PQ curve is 10,000 nits. That's it by definition. Do you remember the PQ curve? Let's see if I can back up and find that.
Oh, yeah.
This, right. So what I did was essentially this. So 100 IRE is here at the right edge. And that's the top of that curve. It's also the top of the PQ curve, the way I did it. And and Dolby says, well, that's 10,000 nits. So that's really bright. So back to, does that help explain that?
Sure.
Okay, so it's really bright. Yeah, remember Dolby says code values, or IRE, now have absolute brightness mappings. And they've got the whole industry thinking in terms of absolute brightness now, whether it's for better or worse. So it's really bright. Well, most displays max out at 1,000. And by the way, that's something new. The system can go up to 10,000, but it's not expected that all displays will show you everything. So most displays just give up at about 1,000. So if I clip this signal at 1,000, oh my gosh, that's what we get. And that's just not useful. It's just not useful at all. So what to do? Well, someone, Lars Borg from Adobe, came by and looked at this and said, well, real world, he said, is not composed of massively bright stuff. It's mostly diffuse reflectors. And the bright stuff are those specular reflectors, those like chrome on things, or Christmas tree ornaments that are bright, or little bright lights or things, glistening water, things like that. That reflect the light directly and are very, very bright. But mostly diffuse reflectors are what we see in the world. So what I had done earlier was I had mapped all these curves to meet at the top, but that's not really the intent here. PQ goes up to 10,000 nits here. HLG is really defined at about 1,000 nits nominally, and 709 is maybe 100. CRTs do about 100. So that's what these curves are. So it's not really fair to map to do this. This is really what we want to do. So what's wrong with saying HDR is just another color space? And Well, scenes are mostly diffuse reflectors. SDR puts these at about 100%. Most CRTs max out around there. SDR had very little headroom for specular reflectors, maybe a little depending how you expose the images. And HDR is not really about just making everything really bright. It's really more about making it sort of sparkly here and there, but not the whole picture. So most of our test patterns should be exposed around 100 to 200 nits. And just a few features should be bright, just like the real world is. So you end up with two concepts of white. You have the 100% specular, which is the maximum thing the system can represent in terms of brightness. But then you have the normal 100% diffuse reflector, like a bright white sheet of paper. And so this turns out to be the number that everyone needs to focus on in terms of exposure, and then let the rest of the image do what it will. So again, two types of peak white. There's diffuse, and we set that around 200 nits. And then there's specular, which could be 1,000 to 10,000 nits, so which gives you about 5 to 50x headroom from diffuse up to specular, or 2 to 6 f-stops of headroom. So instead of this, we end up with this. So most features in this pattern are darker. They're scaled to the diffuse brightness. Again, you're seeing this displayed as SDR because your computer monitors SDR. So just these features are HDR, and they're scaled to max specular reflectance, which is 10,000 nits in PQ. And the rest of it is scaled to 100% diffuse reflectance, which we usually ship at 203 nits. It's a knob on our code. 203 nits, that's a funny value. People were asking BBC, how should we expose? And they said, set diffuse white to 75 IRE on your waveform monitor. It turns out 75 IRE for HLG for 1,000 nit display is 203 nits. And that's where that comes from. I like that question. All right, well, what can go wrong in HDR? And how does this test pattern reveal it? Well, back to our camera display diagram. So we said earlier that HDR requires that this matrix be slightly different. Well, remember the camera and the display and any intermediate processing, they're in different locations. These are not connected. So you just have to get it right at both ends, and it's an opportunity for a mismatch. So you get a YUV matrix mismatch. There's 3 standards actually now for this YUV matrix. There's Rec 601, which is the standard definition, 709, which is associated with high definition, and Rec 2020, which is associated with ultra high definition, UHD or 4K. So how can we detect this? Well, this little red and green ramp feature lets you see that. So that feature looks like this. It's a ramp signal with some added texture square wave thing, checkerboard. And when it gets very bright, at some point, the system will clip it. It's not clipped in the test pattern. It's just the system clips. And with the same ramp is put into red and green. We ignore blue. You don't need it for this. And you can look and see that they clip at the same place. That means it's good. Well, if we run this through RGB to YCBCR and then convert that inappropriately, we screw it up. So it's 2020 this way and then 709 on the decode side. We get incorrect values. What happens? Well, it turns out the red gain is too high. And I'm sorry, the green gain is too high, so it clips sooner. The green gain is too high, it clips sooner. So you can see that the texture vanishes in green before it does in red. And this will show you that the matrix is mismatched. Pretty sensitive detector. The gammas, of course, could be mismatched. This happens all the time. How do we detect that? Well, there are frequency sweeps here. These are sine wave sweeps. Down here, there are sine waves that are linear sine waves in code values. It's like, but here it's linear sine waves in linear light, so they're precompensated by the expected gamma. or OETF curve. So how does that help? Well, you have sine waves in the code value space. They look like sine waves. They're symmetrical. They're equal up and equal down. But then you go through, at the display, you go through the electro to optical transfer function. They're no longer sine waves. They get distorted like this. And this will give you moire patterns, especially in the higher frequencies. It'll look like moire patterns. However, if you precompensate these sine waves with the inverse EOTF, like this, then when you go through the EOTF, you end up with pure sine waves as light. And then the moire actually nulls out when the gamma matches. On monitors with an adjustable gamma, you can see it go through a null. It's a very sensitive way to detect gamma mismatch. I don't know if you can see this where you are. Here I can see some moire here, when these, because they're not sine waves, and up here, the moire, well, I can see a little bit.
Can you describe what the moire pattern is?
Okay, so as these frequencies go from bottom to top, they get higher and higher in frequency, and they should just get very fine and turn into almost gray. But what we're seeing is a lower frequency. You see these darker bands appearing and darker bands here. This is called moire, like also known as aliasing. And it comes as a result of, well, you saw earlier how the is now not symmetrical top to bottom. So you're getting more dark than light. And that appears as moire patterns. But when you have a good monitor, and the reference monitors that Sony and Canon are making do this perfectly well. It's just vanish. The moire, the little dark bands, you see, I see some here. I don't know what you're seeing. And sorry, Zoom may be screwing this up because codes it and turns it into a lower resolution. You're screwed. You can see moire everywhere. And that may be what you're seeing. What are you seeing? Does this area look the same as this area to you?
Does well, the bottom definitely looks different than the top. I'll tell you that.
Okay, well,
but moire is visible in both on my monitor.
Yeah, is it less visible in one of them?
It's a little less visible on the bottom one on my monitor.
Yeah, I see. It's interesting what happens. So,
yep.
But on a reference monitor, it works. It's really quite clean. And the X300 monitor has a knob for adjusting HLG gamma, and you can take it through a null. It's remarkable. So HDR requires 10 bits to the home. So HEVC or H.265 now has a consumer profile that's 10 bits. So we might, now it's important to maintain 10 bits. Otherwise it could get pretty ugly. So do we have a loss of, did we get to 8 bits? 8 bits is a problem. So there's this shallow gradient in the pattern. It actually rotates when the pattern moves. And I don't know what you're seeing through Zoom. Gosh, what I'm seeing is diagonal bands.
Yeah, we're seeing that too, or at least I am.
Yes, I see it too, diagonal bands.
Okay, diagonal bands. And so you'll see banding in 8-bit, but in 10-bit, it should go away. And here I'm seeing it's pretty smooth. So I don't know what you're seeing there.
Agreed.
It's smoother, but there's still a couple gradients I can see.
Yeah, well, there you are. That's, well, Zoom encodes to 8 bits. So I think when I created the slide, I exaggerated I cranked up the gain so it would get through a little bit better, but oh well. Also, color matrix mismatch. And so the simplest way to detect that the color is being interpreted incorrectly is to look at these faces. Human vision is very sensitive to color in the context of a face, unless you're Lars Borg and then you look at the Macbeth chart here. But and maybe some of you have the Macbeth chart in your internal brain memory. If it's matched, the ladies look like this. If you interpret, if you send it as 2020 but interpret it as 709, they look like this, and you can immediately see that, oh gee, we've got a mismatch in the color gamut. 709, correct, incorrect, correct, incorrect. Well, like I said, PQ, for example, defines brightnesses all the way up to 10,000, but now monitors aren't expected to cover that whole range. So how much are they covering? So here's a calibrated stair step, a logarithmic stair step. So it's got the top is 10,000 nits, and then it drops 8,000, 4,000, 2,000, and then repeats that a decade lower, 1,800, 400, 200, 100, 80, 40, 20. This is an 18% chip. Well, I'll get to that. So the little thing, darker things here are a third stop down and a third stop up to give you a couple extra values to look at. And that's an 18% chip. And there's a moving bar that, that looks just like flashing colors here. Thank you, PowerPoint. This worked better. So anyway, how to use this? So a normal stair step looks like this. You can see every step. So what you look for is, well, 200 to 400, that's different. 400 to 800, they look different. 800 to 1,000, that looks different. 1,000 to 2,000, like that looks the same. It's clipped at 1,000. And you can look at the third stop down, third stop up and get a finer estimation of it. One more detail, the optical to optical transfer function, or the overall from camera to display. So the optical to electronic transfer function, OETF, is in the camera, and the EOTF is in the display. The optical to optical transfer function is the whole system glass to glass. You'd expect that to be linear, right? If you're like an engineer like me, we want it linear. Well, it turns out perceptually, not really. You don't want that. A gamma, an overall system gamma of about 1.2 is desirable. Is a desirable look. So that's been baked into the standards. So the OETF and the EOTF are considered inverses. So there's our camera and our display. However, the PQ standard defines an OOTF in the camera. So it's about a 1.2 gamma here. HLG defines a similar thing at the display, however. So, and the amount of gamma depends on the display's brightness. So for a 1,000 nit display, it's 1.2, and there's an equation they put in the standard, which is BT2100, that describes what the gamma should be depending on the maximum display brightness at that receiver, at that TV. So the function of light, the tone scale at the sensor and the tone scale at the display are different. They're not matched. And that's been baked into the standards. That's intentional. So we call this scene referred, right? And we call this display referred. And so when you're converting from one thing to another, now you need to ask, well, are you converting from the display backwards through the system? Or are you converting as if, so you're given code values and you're going to convert it, like we said, at RP177, you have to get to linear light somehow. But what linear light? Because now the display and the scene have different ideas of what linear light is, depending on the OOTF, the 1.2. So, should a test pattern be scene referred or display referred? I went around HPA asking this question and getting really confused looks, which was the intent, really, to get people to think about it. Well, the answer, I think, is it depends. Depends what you're trying to measure. If a test pattern is used to be to evaluate a display, well, then you would want display referred. If you're going to evaluate signal processing after the camera, then you might want scene referred features. So this stair step here is rendered in our patterns as display referred. And the faces here are rendered as scene referred, as is the Macbeth chart, the color checker. Also, this white reference, 18%, 90%, 100%, is scene referred as if it were a white reference card in front of a camera. That's about it. That's about all I have. 10:30. Sorry, that would be 9:30. What time is it there? 7:30. SMPTE 2084 defines the PQ curve, and it's also known as HDR10. BT 2020 defines the color primaries for UHD and 8K scanning. BT 2100 defines the whole color space parameters for PQ and HLG. It incorporates BT 2020 and 2084 and also the HLG, it describes HLG. 2111 defines HDR color bars. Actually, it defines two sets. It defines bars for HLG and bars for PQ. And it sets the brightness of the bars at 203 nits. Remember how many nits is color bars. And BT 248 is an example of guidance for doing live production on how to convert from SDR and HDR back and forth, getting into things like how should the graphics look and things like that. And there's a lot more features to this pattern, too many to get into, obviously, today. So for more information, this is my comrade in arms, Arkady Kopansky. And you can contact him there, or you can contact me there. Thank you very much.
Well, thank you, Norm. I think that was a great presentation. And
apologies, I lost audio somehow.
I didn't, so I heard you, Ken. It's anyway, yes. Thank you, Norm. Appreciate that. That was a great presentation and introduction to the test patterns that you guys have developed and the reasons why you've developed them. It's a great presentation. Thank you.
Thank you.
Does the group have any questions for Norm? And while I ask that question, wait for any responses, I'd like to say that there is a great video on YouTube about these test patterns and how to use them. And it's wonderful. I put it up on my LinkedIn page, and you can get to it on YouTube. I'll try to find a way to send a link to the group, but really walks you through how the test patterns work and where to use them. So we have any questions?
You have one in the chat box.
Yeah, it looks like we got two. When will SMPTE meetings be broadcast in HDR10? Ah, good question.
I'm not sure that's a question directed to Norm, but it's a good question.
Yeah,
I don't know. It's a good idea. It would be great if we can get there. You know, I remember that in presentation projectors in offices were 4:3 for the longest time. And I'm like, when are they going to make them 16:9? Eventually they got there. So maybe eventually we'll get HDR and things like that and computers. It's coming. Apple's doing it.
Eventually we'll get there. Yep. And so there's another question. There's another question here. What does the new encoding do to the visible noise in the display?
You mean like the camera noise in the display? Oh, geez. Sometimes
what does the new encoding, so it's from Bruce. What does the new encoding do to the visible noise in the display? Bruce, can you clarify that question for us? It's
like the camera noise, or?
And what encoding? What new encoding? Feel free to unmute yourself and ask the question live.
Is Bruce still here? I don't see Bruce. Oh, well, I can.
Sorry, can anyone hear me?
Yes.
I lost audio.
We hear you, Ken. Well, I mean, PQ has a very large high gain near black. All gamma has high gain near black. That's the point, because you want to push the quantization steps down. You want to increase the quantization steps near black. So if there's camera noise, you run the risk of cranking that up. So, but fortunately, cameras are better and better. So their cameras are now like 14 stops dynamic range. It's quite amazing. So that's less and less of a problem. In terms of transmission noise, gamma is designed to essentially reduce that. So anything that benefits from reducing noise in the channel, which includes compression noise like MPEG or H.264 or H.265 compression, the artifacts from that will be reduced in black areas to make them less visible, which is really why we have gamma in the first place. We didn't, you know, in the 30s, we didn't have quantization noise, but we had thermal noise. We had, you know, over the air noise, snow. It's the same problem at some level.
I think that covers it.
Thank you, Ray.
All right. You got a couple thank yous in the chat, Norm. People are appreciating the way you presented a complex subject and the tool that you've developed to help us navigate some of the challenges with these new formats. So with that, I think we'll close, and thank you, Norm, again for staying up late on the East Coast to help out our SMPTE section here in Sacramento with a great presentation on HDR and the challenges that we have with it. Thank you very much.
Thank you, everyone. And thank you, Tim.
Thanks, Norm.
All right.
Night.
Take care, guys.